and I'm super grateful. So is our next speaker. Our next speaker's name is Lenz Belzner. Please, let's welcome him warmly.
Hello everybody, thanks for having me. And yeah, probably some kind of really well. So I'm going to speak about distributed autonomous real-time systems. Actually, I'm heading the data science and AI unit at MaibornWolff. It's a professional services provider here in Munich. And I'm actively collaborating with a lot of my former colleagues at Munich on, among the topics we're working on are these distributed autonomous real-time systems. So what are the domains that we're speaking about? In the talk before, there was this kind of two things that were highlighted by Michael Jordan that we should work on. The one is intelligence augmentation, where it's about interaction of humans with machines and systems. And we are into the other thing, it's intelligence infrastructure, where we think about systems that organize themselves, that kind of do want to interact with humans as few or as less as possible. So this is a container site, and there are many cranes and machines that have to organize these containers based on ships that arrive and that go somewhere scheduled. And there are a lot of decisions taken at every step in the process. So where to put the next container, some ship arrives late, how to rearrange the containers in order to minimize cost, in order to minimize the time it takes to load the next ship that's waiting in the line. Similar problems that we can imagine of this kind of factories that arrange themselves, production line optimization, or fleet management, for example, if you think of car sharing fleets. Another kind of domain that we're thinking about is traffic, in particular autonomous traffic, and for now we're in the process of creating cars that are able to drive autonomously in everyday traffic, but there's also effort in order to kind of get these individual cars communicate with each other in order to cope with the constrained resources like traffic lanes that are available. Another system that is of this kind is smart grid energy, where many participants are competing for prices for a market that has to be kind of delivered, and the question is always how much energy to produce in order to not break the whole grid system down, or how much to store in order to save labor and so on. So the approach that we are taking, and that is possible in order to make these systems take decisions on their own, is that we're building a simulation, a digital twin, they call it, in order to search in this simulation for valuable sequences of actions in order to maximize some value of interest. For example, maximize the kind of benefit, the kind of revenue you get from producing a particular number of items in a factory. Speaking of which, as academics, we tend to oversimplify problems a lot, but this is a very simplified problem, a very simplified model of a smart factory. So we have a particular set of machines that can perform different operations, and they are connected by some kind of physical topology. And in this factory, there are robots that transport items to be produced. And each of these robots is equipped with its own decision mechanism. Okay? So the question each of these machines, each of these robots has, is where to put my item next, given all the other guys that are also transporting their items to the production machines, and how do we cope with the kind of emerging complexity that's up in this problem. So this is a very small set. You can imagine that in real-world problems, there are many more machines and many more agents, and we also scaled this up in our experiments. And this is also as kind of was created in collaboration with some large real-world participants who said, okay, if we model it like that, it kind of fits into our supply chain management with logistics problems, and we can think about the transfer to real-world applications. the way we tackle this kind of problem is reinforcement learning. Who heard about reinforcement learning before? Okay, that's good. Who heard about reinforcement learning playing Go? Okay, that's good. So I think 2 years ago, or last year, the guys of DeepMind, they invented a kind of program that was able to play Go better than the world champion. And what was fascinating about this is that Go has been kind of declared one of the grand challenges of artificial intelligence, because there is so many decisions that can be made at each step in the game, and each decision has a long-term impact on what decisions can be made in the future. And so humans were thinking that will still take a long time until the machine is able to play this game better than human champions. It came different. AlphaGo was beating this human champion, I think 4-1, 5-0, and the latest. So the first iteration, I think they bootstrapped it with human expert moves from a database. Okay, so they started to learn a policy strategy for Go based on human moves, and everybody was like, without human creativity and bootstrapping, this would not have happened. However, the guys of DeepMind found out that it's even getting better if we don't bootstrap it with the human experience. So I think this is a very fascinating approach. And basically, how does this work? It's very simple by concept. So there's an environment. In the Go case, that's the game, and the environment emits two signals to an agent. That's the player. It emits the state. So where are the Go, stones, and it emits a reward. In the case of Go, I think there's a single reward at the end of the game. You won or you lose. That's it. And the agent emits an action into the environment. It's like where I put my stone. And the basic idea of reinforcement learning is we follow the circle all the time, use some fancy technology, backpropagating the reward signal into the agent over time in order to make it emit actions that yield rewards which maximize. Okay, that's the basic idea behind the reinforcement learning thingy. And it works astonishingly well. At its core, it's a try and error method. I won't go into all these algorithmic details that play behind here, but there are some tricks the guys of DeepMind use to make this AlphaGo algorithm work quite well. So in the first place, they said, okay, we take this artificial player, randomly initialized, not knowing anything, and we let it play against itself. So in the beginning, it's two stupid guys doing random stuff against each other. And then they use this data where by chance, some kind of rewarding strategy or signal may appear, and they compile this by learning, by retraining their self-play strategy. And so the hope behind it is that the agent finds the kind of informative parts in the games they play randomly in order to improve. And in the end, they take the old network, initially random, later on a little better, and the new network that was trained with the new information from the self-play thingy, and they pit it against each other. Okay, and only in case the new network, including the data from the retraining, is better than the old one gets replaced. And the effect of this is that this yields a natural curriculum for the learning system. Okay, so the enemy is always around. So as it's playing itself, the enemy is always kind of as hard as you can get, and only if the guy that's a little better. So the problem of declining again is not given here. So how does this self-play thingy work? The idea is that at each stage in the game, the system uses this digital twin, this environmental simulation, and plans up to some kind of terminating horizon into the future, and then it uses the information of this plan to decide on an action, do a step forward. And then it repeats this, and repeats this, it does this again and again. And it does this by using Monte Carlo tree search. Here, the idea is not to exploit the whole search space at once, but to incrementally kind of emphasize the search into regions of the space of possibilities, space of game outcomes that are kind of promising. So this is a statistical technique. And what's important to note here for the later messages, at each node in the tree, the state of the game is kind of stored, and then we have edges which kind of represent actions that we can take, and at the end of the actions that were taken, there's a new state to be stored, and the Monte Carlo tree search maintains some kind of statistics which are used in order to decide where to expand the tree in the next layout. This is again pitting. It's just to remember that this is an important part of the AlphaGo algorithm. You take the two players, the old one and the new one, and you only take the new one for the next iteration to generate your trigger data if it's better than the old one. So the question that we are actually dealing with is how does this idea, how does this technology fit into the kind of problems that I was outlining in the first place? Many agents, stochasticity, so all these things that are kind of making it AlphaGo as it is unfeasible or not applicable right now. So multiple agents means there are different individuals that are each of them is interacting in this kind of reinforcement learning way. So in our picture with the environment, in the states and rewards, it looks like this. We have still the environment, and now it emits a state and then a reward to each of the agents, and the actions that each of the agents kind of emit, they are combined to one joint action that is performed by the whole team. And the other thing that's making the multi-agent problem very complex is, or the kind of domain very complex that we were speaking about beforehand, is that there is stochasticity and uncertainty involved here. So we're not always knowing when the next ship is going to arrive. We're not always, so a machine that produces some item can take longer than we thought it would take, and something like that. And the effect is that the branching of the states, so the size of the resulting state space, is even orders of magnitude larger than in the Go game. So, let's skip that slide. The core idea that we used, or how we extended actually the basic mechanism of Monte Carlo tree search for dealing with this kind of state space explosion, is taken from control theory, and there's an approach which is called open loop planning. And open loop planning does something very fascinating. It skips the conditioning of the search on the states. So it just compiles the selected actions and statistics on those, and it skips the information on the states that that these actions led to. Okay? And the other thing that we were kind of taking up is, like, we were thinking, how could we resemble this self-play, this boxing scenario in a cooperative setting, like in the factory, where we have many machines, which each of them is deciding, but they have a common goal, like don't interfere with each other. So we train a population, a team of networks, and for each player, for each self-play iteration, we just select some guys. So it's like with a sports team, you rotate. You bind is, I think, an expert in this kind of training or challenging people. So they don't learn to interact with each other perfectly, but they learn to interact with many different others quite well. And in fact, in our experiments, we were able to run 100 agents physically distributed, and they were performing as well as, for example, when only running 20 agents, which is a good thing. And the other result is, so the basic line down here is 2 state-of-the-art algorithms from distributed open loop control. And when we kind of included this data-driven learning that is at the core of AlphaGo, or reinforcement learning, we were showing that we were greatly outperforming it in terms of effectiveness. Okay? So what we are thinking about here is, like, we're making cars autonomous, we're already flying with planes that are doing a lot of the work autonomously, and we should and we can think about automation in large-scale distributed systems. What's the time zone? Okay, so there's a second problem or kind of interesting problem arising when we're thinking about this kind of problems, and given the fact or the probability that we can use kind of these automation techniques in distributed systems, we can think of non-collaborative systems because, for example, traffic or this energy grid thingy, there are many participants and they're not, so if I drive with my car and I want to go to my target destination and you drive with your car and you want to go there, it's not necessarily the case that I care about how long you take there. So if there's kind of a scarce resource, like the direct way, and if we both go in, then there's a traffic jam. If one of us goes around, and then there's more traffic jam, but in the end, we arrive both faster than when going both on the direct way. Okay, so that's very simplified. And yeah, that's the two domains. I preempt my own slides. And so what we were thinking about, so one of my collaborators came up with a economics background, and he said, what about making agents able to share some of the value they get from taking a decision, okay? So this is an action, and this is a utility, so what I personally get from doing something, and we extended this action thingy by some share. So the agent does not only decide, okay, I go to this machine, or I drive through this lane, but I have some kind of, budget that I can spend that, depending on the things I earned before. And the value I spend, it detriments my gain. However, I get a fair share of all the shares that have been made. It's kind of a communistic reinforcement learning system, if you want. I think Karl Marx had his 200-year anniversary or something like that. So here below, we see in a very simplistic example what this means. So there's a yellow guy and a blue guy, and there's a resource. Yellow car, blue car, and there's the direct way. And maybe the value of the direct way is different to us. Maybe I'm in a hurry, you're not. Then it's very valuable for me to take the direct way, and you may say, okay, I could go around the other way. So if we don't share, and the distribution takes place 50-50, then the expected global value is 1.5. And if I'm allowed to share, to use some of the time I get, for example, in money, then the expected value is 2, which is better. So we did this in different kind of stylized environments, and we found 2 very interesting things. The first thing we found is it works. Okay, so what we see here is kind of the learning evolution of our system, and in the y-axis we see the global return that was generated by the decision made by the guys individually. And the different colors are indicating different fractions of agents that are willing to or able to share. Okay? So the lower curve is nobody's able to share. This curve is 60 of 100 guys are able to share. And this curve is everybody is able to share. And what is interesting about this is we did not tell the agents share. We just said if it's helpful to you, you may share. And they found out sharing is a cool thing. So that's the one thing. And the other insight, so this is kind of a technical plot, but when we think about what's happening, or if we compare kind of the individual values, so this is the global gain, what everybody gains, and this is what every individual gains, and the blue boxes are showing the kind of gain you get if you're saying, I'm not sharing, because what should I? And the green boxes is the individual gain that you get, empirically get, when you are able to share and use this learning mechanism. And for example, here, nobody may share, this is the expected value. 20 guys may share, the other guys defect. Then we see that the sharing guys are exploited by the defectors. If you go all to the right, nobody's defecting. You get the most overall if you're sharing. So each agent could ask a question to itself. What should I do? Should I share or should I not? So actually there is no rational answer to this. We're still in the course of exploring what happens here. And so because what happens if I defect, okay, if we hear that's bad. So if we observe what's happening here, then at each point in the system, there's a situation where defection is a good idea because individually I get more, but the whole thing declines, and the other way around. If we decline enough, then it's a good idea to start sharing again.
So, wrapping it up, one last thing. So you may be thinking about the sharing thing as a kind of a fancy idea. However, 3 days ago, I found out that I think Bosch is already exploring using YOTA. This kind of machine-to-machine Bitcoin thingy. I'm not an expert in that, but they're using that for their in an exploratory way for their production line ideas. Okay, so what were we speaking about? Large-scale artificial intelligence infrastructure problems, multi-agent systems, and we can take fancy algorithms like AlphaGo and use these and extend these approaches in order to tackle this kind of systems. So that's the goal: make it large-scale and distributed. And in the course, when we're thinking about this kind of problems, emergence is a critical thing that we should think about because it yields problems that we have to think about on an ethical level. Okay, this is a societal decision that we have to take. How to deal with that? So that's it from my side. If you're interested, get in touch. Thank you very much.
We have time for a couple of questions.
Yeah.
I want to be sure I understood you correctly. So you said agents tend to be sharing, right?
Excuse me. They tend to share.
They tend to
Yes.
share, right? But if you don't have any reward or punishment for sharing, did you look at the pattern how they, what was the reason that they began with this tendency to share?
So, yes, and I oversimplified. It's not always the best solution to share. It is only the case if an individual can generate more as an individual reward in a particular situation that when both are kind of acting on their own behalf. Okay? So there are some kind of mathematical preliminaries that have to be fulfilled, constraints that have to be fulfilled in the problem domain, that the agents find out that sharing may be a good idea.
So then it's rewarded.
Excuse me?
It's implicitly rewarded.
So it's the shape of the reward landscape in the matrix. However, we're still in the course of finding out whether sharing as an option hurts in the other case. Because it's a free parameter that has to be learned, so it may slow down the learning process. However, if the learning is kind of well defined, then everybody should learn that in a situation where it's not valuable to share, why should we share? Yeah.
You go through the model with different value drivers. So it could be, for instance, one value driver time and the other money. So
Not yet. Yes. Interesting point. Not yet.
because when I look in the future, streets should be organized like this. You shouldn't pay tax.
Exactly.
It should be taxed by.
Yes. I think this is also scratching a very fundamental point of these kind of technologies. For now, we have to put a number on the kind of value that we want the agents to optimize. So the process of formulating this number is it's a hard question. As soon as you get to what's time worth or so, you know? That's a political decision maybe or so.
I mean, on the other hand, when I think in aviation, I have costs. So even at the cost.
I saw some other questions, and there are so many guys, and some of them maybe just want to leave or have some beer, so we can chat over this.
So in the graph you showed previously, I think you could see that all the agents that could share performed worse on average.
Yes,
than
individually that is the case.
But you also said that in principle they can learn that to not share. So wouldn't you expect, I mean, the sharers have in principle more options.
Yes.
Shouldn't it be at least as good as the default? Because the sharers could just learn like, oh, sharing is a bad idea.
Yeah, that is a valid point. Actually, the numbers that we see here is at a given point in time. And I kind of abstracted away the temporal evolutionary dynamics of the. So you're speaking about at some point, that's true. However, if they are here, in principle, if they explore enough, they find out that if everybody's sharing, sharing is a good thing. So if they are here, they eventually find out that if some of them find out sharing is a bad idea because I get more than the share as if I defect, and then they go back here, and this is kind of an evolutionary process which is oscillating probably, and we're still thinking about how to go into this.
The agent can share, doesn't take it into account, like an estimation of the behavior of the other agents, like that they also share or not when they
That's
decide what to do.
an excellent idea. I was visiting a meetup some weeks ago where I think Jakob Förster from OpenAI or so spoke about Lola, and they're actually pursuing this idea like learning better by building models about the learning of the other guy and making that differentiable in order to use this neural network thingy. And this is a brilliant idea to bring into this year. Yeah. So we're not doing that yet. Not at all.
Yeah, it's the same in game theory. If you expect your counterpart is acting hostile, then you have to act differently.
Yes.
And so in the end, you might get less reward.
Yes.
When you act in this way, but your counterpart acts not so hostile, then you could get a higher reward.
Absolutely.
And you act more random.
I hope that this is the way where I want to get personally. I want to get here. Okay, I want to build systems that are able to figure out ways which stabilize in this state, where there's no incentive to kind of drop the global value for an individual. I fear that may not be possible in all real world situations.
Final question.
Yes.
Okay, because you just mentioned that you want us to get to that point, but according to game theory, you will not get there. Because by minimizing costs, you will get to the pseudo maximum position where nobody will share, because you cannot rely on something that can happen or cannot happen. So you will fall back to the worst behavior from the other agents. So each agent should actually then select the no sharing behavior, so to say, right?
This is true in classical game theory. However, we are thinking about a formulation. We're not there yet. But we're thinking that allowing agents to share is a way of changing the game that is played. And the idea is that we can use, so what the sharing guy is doing actually, he's playing reinforcement learning with the other agents. He changes the reward signal of the other players. So if you think of it in a game theory matrix, you change the game matrix. You learn how to change this. And the hope is that there may exist a matrix where Nash equilibrium or dominating strategies always correlate with global.
This is basically the only way to get out of the cell, of the prison cell, so to say. Because otherwise you will be in prison.
Yes.
And yeah.
Thank you, Lenz.
Guys, we would like to thank all the sponsors and participants and the speakers for attending MI Summit. the one and only free event in Munich regarding artificial intelligence. It will become even bigger for the next years because we believe that the science should be hip and free.
Yay!